Okay, so remember we've been calculating the Hamiltonian, and we've actually only been considering a single term. Okay, the term that we've been considering is this 1/2 pi squared term, and we've just evaluated the integral over d3x. So that's what we've been busy with, evaluating this integral. And for this particular term, the answer that we have is summarized sitting over here. K1 appears, K1 tilde appears, so we've defined K1 tilde, and omega K squared appears. Now, you would evaluate the remaining two terms, this term here, which is from the gradient dotted into the gradient, and this term here, which is the m squared phi squared term. And what I'm now going to do is I'm going to write down the answer that you would have gotten if you had included the green and the gold terms, okay? And done the integral d3x. So let's start doing that now. So we'll just put the answer down below here. So h is equal to, so this is the 1/2 sitting up front that we see from the top there. There's an integral d3 K1 to pi cubed to omega K1. And then we've got 1/2. Now, the first thing that I'm going to do, just because it makes the manipulations that follow slightly easier, watch me carefully now. Notice that in this answer that we got, sitting in the measure, we've got 1/2 omega K1. Then the first term, so there it is sitting over there in the measure, the 2 omega K1 in the denominator. Then inside the first term, we've got an omega K1. Inside the second term, we've got an omega K1. And in the third term, we've got an omega K1. So in actual fact, those omega K1s cancel out completely, okay? They would completely cancel. Equivalently, I can change this to an omega K1 squared, as long as I put a squared there, a squared there, and a squared there. The omegas cancel, but so will the omega K squareds. And this is just going to make it slightly easier for me to write down the answer that I'm going to write down now. So starting off with the pi squared contribution, okay, what do we have? Well, from the first term above, we've got minus omega K1 squared. So this term that I've just written down comes from there, that we actually evaluated, okay? And I'm telling you that if you go ahead and you evaluate this divergence of phi dot into the divergence of phi, you will find plus K1 dot K1. So this comes from the divergence of phi dotted into the divergence of phi. And then if you add in the 1/2 m squared phi squared term, what you will have contributing is plus m squared. So this will come from the m squared phi squared term. And then we will still have the e to the minus 2i omega kt and a K1 or alpha K1, sorry, let's write that correctly. Alpha K1, alpha of K1 tilde. So this is the first term, okay? Now let's go to the next term. Good. So we'll have plus. So we've got an omega K1 squared. And this comes from the pi dot pi. So this term that I've just written down here is that term sitting over there. If you were to go ahead and evaluate the gradient of phi dot into the gradient of phi, you'd find a K1 dot K1, okay? So that term comes from the gradient of phi dot into the gradient of phi. And if you look at the m squared term, you'd get an additional plus m squared. And that's that term sitting over there. And now let's complete the term. Looking back at what we evaluated, we know that this gets multiplied by alpha dagger of K1 times alpha of K1 plus alpha of K1 times alpha dagger of K1. Good. Oh, and that's a square bracket. And now we've got the final term. So for the final term, we start off with an minus omega K1 squared. So again, this comes from the pi squared term. That's what we evaluated. So there's the omega K1 squared. Then we've got plus K1 dot K1. And this we get from the gradient of phi dot into the gradient of phi. And then we've also from the mass term got plus m squared. And that's from the mass squared term. And now let's finish off this term. This gets multiplied by e to the 2I omega kt alpha dagger of K1 alpha dagger of K1 tilde. And that is the answer for the Hamiltonian, okay? So let's just review quickly. So we started off with the expression for the Hamiltonian. We plugged in the mode expansion for the field phi and the mode expansion for the field pi. We then did the integral over x. That gave us a delta function of momentum. We then did the integral over momentum, and we got this result over here. Now, we actually only did the integral over x and the integral over momentum for the pi squared term, but I've told you what the answer is for the gradient of phi dot into the gradient of phi term and for the m squared term. So this answer that we've written down at the bottom of the page over here, well, this is for the whole Hamiltonian. Now, this does not look very promising at all. What's wrong with it? Well, this is the Hamiltonian. This is meant to be independent of time. But look at the first term, the alpha term. That's got an e to the minus 2I omega kt, which certainly depends on time. And the third term here, the alpha dagger term, that's got an e to the 2I omega kt, again dependent on time. But something comes to the rescue to save us. And probably you've already seen it. We know that omega k squared is equal to k dot k plus m squared, which means, let's write it in a slightly different color. This means that minus omega k1 squared plus k1 dot k1 plus m squared, this is equal to 0. So the last term cancels out and the first term cancels out. This is great because that's all of the time dependence gone. The other thing that we know is that omega k1 squared plus k1 dot k1 plus m squared, well, omega k squared is k dot k plus m squared, so this is just 2 omega k1 squared. So we can simplify the remaining term in the Hamiltonian. And what do we get from that? Well, we learned that now the Hamiltonian is equal to 1/2. There is an integral d3 k1 over, we have a 2 pi cubed. We've got 2 omega k1. So that's just the measure sitting there. And then we've got 1/2 times by this bracket, which is 2 omega k1 squared. Well, oh, sorry, guys, I screwed up. What did I screw up? Lucky I noticed it here. With the measure, we changed the omega k into an omega k squared. So sorry, this should be squared. That's the manipulation that we did just to make things simpler. And this should be squared, okay? So go ahead, do all of the integrals. We only did the pi squared integral, but do all of them, and you'll get the answer that I'm writing down now. And then this round bracket over here is 2 omega k1 squared times by the 1/2. This just gives us omega k1 squared. And then this is multiplied by alpha dagger of K1 alpha of K1 plus alpha of K1 alpha dagger of K1. And the 2 omega K squareds cancel. So let's just summarize our final answer for the Hamiltonian. H is equal to 1/2 the integral d3. I'm just going to say K because we needn't say K1 anymore, over 2 pi cubed to, no, that's not needed. That's all cancelled. So let's tidy this up a little. And then we've got alpha dagger of K1, alpha of K1 plus alpha of K1, alpha dagger of K1. What a lovely, simple result. And I just want to stress one thing. The only place where really you had anything to remember was in the very first step when we did the integral over x. And remember that when we did this integral over x, we used the answer for the integral of an exponential. So the formula that we used, and I really want you to commit this to memory because it is such a useful formula. The formula that we use tells us that the integral d3x of e to the I k dot x, so please remember this formula. It's 2 pi cubed times by delta of k. And if you complex conjugate this formula, you can easily show that this is also equal to the integral d3x of e to the minus I k dot x. You are going to use that integral formula again and again and again, so please remember it. It should look very sensible to you. You see, remember that delta, when k is equal to 0, so delta of naught, well, this we know is infinity. But if you stick in k is equal to 0, well, you're integrating the integral d3x of 1, and that's obviously infinite. Whereas the delta, when k is not 0, is equal to 0. And the integral d3x of e to the I k dot x, well, here you are integrating something. So I'm just going to draw a cartoon. You're integrating something that keeps oscillating. But what's the integral of an oscillating function? 0, because you catch the same amount of area above the curve as below the curve. So that's why this integrates to 0. So it's very easy to understand why the integral d3x e to the I k dot x is proportional to the delta function. The only thing that you have to remember is the 2 pi cubed. That lets you do the integral over x. Then you can do the integral over the first momentum using the delta function, and then you get the answer shown in the red box here. Great. We'll interpret that next.